मधुर मनोहर अतीव सुंदर ये सर्व विद्या की राजधानी राजधानी।
Well, my dear students, we are now again to the lectures in the series of technology of metal forming. In this lecture, we are going to speak on wire drying process, which is a very important process in metal forming. The wire drying, you might have seen the wires of different diameters of steel wire, stainless steel wire, copper wire, very frequently used in electrical wirings. A wire which is just like a hair diameter, and the other aluminum wires. So different alloys wires are there, and even the spring wire. So how have you ever thought of how these wires are being produced, how these wires are being manufactured, that is available in market in bulk? Have you ever thought of this? So today in this lecture, so we are going to cover some of the topics which is related to the wire drying. Usually, you know, the wire drying is carried out at cold conditions, but it can also be done at some warm temperature as well. So let us see and discuss all these issues. So as far as the topic is concerned, we are going to deal with the drying process, especially how it looks like, what are the components of wire drying, then the drying practices, and what are the common defects that we come across in wire drying, as well as the residual stresses, how it looks like, and how one can make use of these to ensure that there is no defect and there is no breakage of the wires frequently. And we would also see the drying equipments generally used for manufacturing of wires of different diameters. Alright. So to speak with, let us look at this slide. So you can see here wire drying. The one should not confuse that the drying of cups. So that comes into sheet metal forming processes. So here we are going to speak especially on wire drying. So what is wire drying? Especially if you look at, it is a process where a cross section of solid rod, wire, or tubing, even tubes can be drawn, is reduced or changed in shape by pulling it through a die, through a given die. So look at this figure, which is at the left corner. The number 1 shows the mandrel. So this is especially for drying of tubes, and the number 3 shows the tube, and this number 3 tube, which is input to the die, wire drying die, and you have a mandrel number 1, and 2 is the die. When on the other side, when this tube is pulled, you are going to reduce the diameter of 3 to a lower diameter through a die by pulling action. So one has to compare with the extrusion where you push the input material or the billet, but where in case of drying you pull the material. No doubt there may be back tension and forward tension. So once the coil, this is the input coil you see. So this coil, if it is at the input side, it will create some uh, tension, right? And if it is at the similar coil, when it is after wire drying, when it is wrapped around, then will also be there is a back tension. Okay, so starting with these issues, that as a drying process, wire drying process, what happens in this process, in fact the cross section of a round rod or wire is typically reduced or changed by pulling it through a die, right? And the die angle has great influence therefore on the drying force and the quality of the drawn products. So if the surface of the drawn product is good, shining, then the die angle is very important, and as well as the speed at which the drying is being done. So if you look at this figure where a usual die angle alpha is shown and A0 is the cross sectional area of the input, right, wire, and you come out with the AF as the final cross sectional area of the wire, and you have land again. In fact the die which is used for wire drying and the die which is used for extrusion, especially for drying solid rods and all that, is quite similar. The only few difference we will discuss here. So as a very vague, how do you calculate drying force? So calculating drying force is very important, wire drying force, because accordingly you have to select the pulling force, and so the drying force F, which is given here, is the capital Y average AF, natural log of A0 by AF, where Y average is the average tube stress, true stress of the material in the die gap, right? So that's how these are the variables. If you look at this figure, the process variables in wire drying. So the process variables are the die angle, the reduction in the cross sectional area per pass, the speed of the drying, the temperature, and the lubrication. These all affect the drying force capital F therefore, right? So you can see there, as far as a usual drying process, wire drying process, look at this figure. So usually the whole drying when we take, and if the reduction is large, so you go for the multi-stage drying. That means multi-stage drying means for each stage you have a the input wire, right, and then it passes through a die, and then it again comes to the finishing draw block where you dry it again on the block. So these three things are very important. But when the reduction is large, and if you seek very high production at very high speed of wire drying, then you go into the multi-pass wire drying operation. So this slide usually shows a 2-pass wire drying process. So if you look at, there are components as the wire drawn, and then you have the dies for the first pass, and then the draw block for the first block. So once it comes out, then this draw block, it is again taken back to a sieve and a speed control wheel that is shown here, because when you go to the second pass the speed is different. So the purpose of the sieve and the speed control is to control this speed, this velocity discontinuity, so that you are well ready for the input material at the second stage, and that's how you go on adding the multi stages like that. Okay, so in fact sometimes it is required that when you go from one pass to the another pass, you may require annealing if the material, because wire drying is generally a cold process, so it may so happen that because of the strain hardening the material gets hardened, so there the chance of breakage of the wire may be there, so you need to anneal it. So if this happens, then there is an annealing arrangement as well as, and that can be in the form of coolant as well. So that arrangement we will see just after this. But if you look at the dies, the die is the very important part, as I told, in wire drying. Usually a die in wire drying has got four major area as shown here. You can see if the die thickness is capital H, so the four areas are marked here as the entrance, the reduction where the major forming takes place of the size, and the bearing where the sizing of the final dimension take place, and exit it acts as a relief, right? So you look at these pairs of the dies. So the dies inside it is very finished in such that friction must be lower, least rather. The speed may be of the order of around 300 meter per minute or higher sometimes also. So if at this speed there is some breakage because of the many reasons, it is not good, and it will suffer the production rate as well. So the whole purpose of wire drying is to understand what happens with a good die design, so that there is no breakage and there is longer life of the die as well. So these are the some of the issues we would discuss. As far as continuous wire drying is concerned, as I told, you have this slide where you have the capstan drum that holds multiple loops of the wire around, and initially the wire stock is in the form of coil, so it is taken up. See, the first stage velocity is V1, then it passes through the lubricant box where solid lubricant generally in the form of powder is used, and it has two purposes, the lubricant. So the first purpose is to provide cooling, and second purpose is to provide lower friction, and it is in the form of powder. So there is a draw die inside, and you get the output velocity as the drawn, and then the pulling force certainly capital F, and then it again goes to the another set of the pass, and likewise it continues. So that is how the wire drying passes from the first pass to the end pass, and the diameter goes on decreasing and decreasing, and the velocity goes on increasing and increasing therefore. So the balance of the velocity is very important between the two passes, because if there is any imbalance, the at such a high speed the wire is going to break, and you will hang up with the whole process of continuity of the wire drying. Alright, so as I told, in a similar fashion you can even draw tubes. Usually the tube dryings are very popular. If you look at the refrigerator tubings, this is all produced with this, and in fact there are three types of drying operations, especially the tube drying, where you have a die, and then the stationary mandrel you put in the first case and the die. Secondly, you may have a mandrel which is fixed mandrel, and it is a plug type mandrel, which is in C, and D could be a moving mandrel like here. So this shows the example of tube drawing operations with the and without internal mandrel. The first A is the without mandrel, and the other three cases are with mandrels. Note that a variety of diameters and wall thickness can be produced from the same initial tube stock which had been made by other processes. So you have a tubes, and then you further reduce of the different thickness and different diameters by varieties of these tube drying operations. So what we observe, the wire drying is very interesting, and you know the uses of wires of such a different variety of such a different, and for the electrical industries, for your structural engineering, civil engineering application, it is very used, and therefore when you draw wire, it is always necessary that the wire drying force is less, and that's how your whole purpose must be to reduce the friction, and therefore you require a proper lubricant. So when we come across some different lubricants, proper lubrication is very essential in wire drying, and in order to improve the dye life and reduce drying force and temperature, and with the improved dye surface or the surface finish of the wire, these are the main aim for a good lubrication. Generally we come across 4 different types of lubrication, and accordingly the name of the wire drying operation comes in. Like we may say the wet drying. Okay, the wet drying we call when the dye and the rods are completely immersed in a lubricant. In the previous slide, if you see the box, the lubrication box, so if the dyes and rods, that is the input wire rod, is completely immersed in the lubricant which is wet, we call it as a wet drying. Secondly, when the surface of the rod or the wire to be drawn is coated with a lubricant, we call it as a dry drying. Okay. In third case, we call it as a coating, that is the rod or wire is coated with a soft metal that acts as a solid lubricant. Okay. The fourth one is very interesting, that the ultrasonic vibrations are also sometimes used of the dyes and mandrels, so that it acts as a vibrating, very high speed vibrating, and that adds in to the reduced friction. So one can say also that the ultrasonic vibration can also be used as a lubrication. Whenever you draw wire draw, either tube draw, what is the whole purpose? The purpose is that the drawn wire has a good surface finish. It does not have any kind of defect. Usually we come across the defects and the residual stresses. If any residual stress is left into because of the improper dye angle, because of the improper process variable, then the residual stresses causes a very detrimental defects. Usually the typical defects in wire drying are two nature. Number one is the central cracking, and another where the seams are formed. You look at this figure where schematic illustration of roll straightening of a drawn round rod is shown, and therefore to reduce the these defects, central cracking and seams, you also prefer to straighten the drawn wire properly, so that the seams etc. is not formed, and there is a different arrangement for whole set of the arrangement, where there is a drive chain, there is the cold drying trolley, you have the gripper and lever, you have drawn shape, and then all those things which is shown here. Okay, so like in extrusion, right, sometimes it may so happen, like in extrusion, the central burst, right, like then there is a funnel formation. So that is entirely different, because there you have a compressive stress, but here you have a tensile stress, right. The dies has got compressive, but you are pulling it, so you are under the wire is under rather the tensile stress. So look at this figure in a very usual manner, where you have a wire drying machine. So a wire drying machine, especially for single pass, what it has two major things. One, if you look at the raw coiler, and then the second one, the final coiler, where you get the wire after drawn, and in between there is a die arrangement. Okay, as said. So a wire drying machine consists of these three minimum components. Nowadays the speed control and all these things, and even the annealing facilities are also there available with modern wire drying machines, to ensure a very good quality of wires being drawn. So look at this figure, where usually used for a multi-pass wire drying machine. So you will see it is start from one end, and then it passes to the multi-passes. Then there is a straightening arrangement, and then it goes to another set of. So it's an example of a continuous wire drying process. Okay. So you can draw wires of copper, you can draw wires of aluminum, steels, brass, and all those things. Mainly the material should be has got a good ductility, and it retains its ductility while it is being drawn. The chance of strain hardening should be minimum, because that will hamper the load requirement as well as, and the chance of breakage as well as becomes higher. So usually, as I said, the process variable, because the whole purpose in wire drying is to have a good production rate. With very high speed, let us dry the wires. So the process variables in wire dryings are the die angle as such, the length, then the input wire diameter, then the output drawn wire diameter, and the different components of a die just now we would see. So you have the temperature is also very important, as I said. Usually wire drying is carried out at room temperature, but you can little bit heat and get the advantage of reduced and increased ductility and the lubrication. So you would require less drying force, capital F. So as far as the dies are concerned, as usual compared to the extrusion dies, wire drying dies are quite different. So these dies, wire drying dies, has got entry region, which is funnel like, and lubricant is inside, so that into the die. So through the entry region, that is that funnels the lubricant into the die to prevent scoring of the work and die, right. Then there is another part, if you see here, the approach. Approach is the cone shaped region where the drying takes place, and then the bearing surface that determines the final stock size, and the back relief is that is the bearing surface where you have the exit zone. It provides with the back relief angle of around 30 degree mostly. In usual wire drying dies, the approach angle is of the order of 6 degree to 20 degree, and the back relief, as I said, it is of the order of 30 degree. Then this gives a better uh, uh, dye, having good dye life and other properties. So look at this figure where the dye for the round drying has been shown. So this terminology, what are the different terminology used for drying wire drying? Either you draw wires or rod. As I said, the rod has got larger diameter, the wires has got very reduced diameter. So usually you have bell, that is a radius is provided at the entry, and then you have entering angle, then you have approach angle as shown the middle portion, then you have bearing surface, that is called as the land, and the back relief, so that this die is a usual tungsten carbide die insert. Generally the approach portion where the actual fall deformation takes place, it can be replaceable, made so in the form of die insert. So we use a steel casing, and the diamond dies, generally it is used in drying thin wire, are encased in a similar manner over a casing. So you can see here that is the steel casing, and you have tungsten carbide inserts near the approach portion, and that angle, that is also called as nib. Okay, so the making a wire drying die is quite difficult, and the accuracy required, it must be very high, with very high toughness as well as least wear property, because the wire is being drawn at very high speed of the order of 200 to 300 meter per minute. So if so happens, the chance of wearing of the die and changing of the diameter may take place. So the whole set will get disturbed. So the wearing properties is very important, and that governs the die life. Okay. So as far as the production of pipes, tubes and wires are concerned, it is quite similar here. Like here again, how do you have the steel casing, and in the casing you have the whole carbide die. So this carbide die has got 4 regions. So the bell radius you have, then entrance angle, you have approach angle, and then you have the land, and then you have back relief. So these all items has to be accommodated with the carbide die in a very small region, and that's how the production of manufacturing of this die is very difficult and very challenging, because the cost to at a reduced cost, the high die life is the requirement. So this is what again showing the things how it is going to take place in wire drying. So you have the input incoming wire, then you have the draw block, and then you have the speed control sleeves, and the again die, and again draw block, again sleep control, speed control sleeves, and then likewise in case of multiple. So you see the die and the lubrication things that is happening there. As I said, the wire drying and bar drying is two different areas. So what's the difference between these two? So the difference between the bar drying and the wire drying is only because of the change in the size of the stock. Okay. In case of bar drying, you have larger diameter bar and rod stock, right? In case of wire drying, you have a smaller diameter stock, that is wire size, which is drawn to around 0.03 mm is possible. So although the machines are the same, the methods, equipment and even terminologies are very different when you go for the wire drying or when you go for the bar drying. Alright. So as far as the drying practice is concerned, this is, and the related products when you produce by different practices is very important in industrial aspects. So as far as the practice, drying usually performed as cold, as I said, wire drying cold, and most frequently used for round cross sections. But it has been observed that the wire drying can also be done at warm temperature and with slight variation in shape, like you can even produce a wire which has got cross section of say elliptical shape, right, and different other shapes also. So that is a different category we call as the shape wire drying. But as far as the complexity of the shape is not very high as in extrusion, right? So as far as the drying practice concerned, I told you perform mostly in the cold condition and for the round bars, but shape wire drying at slightly warm temperature is also possible, and it is sometimes done also. As far as the products are concerned, all of you are aware of the wires, whether you take electrical wire, whether you take wire stock for fences, whether you take the coat hangers wire, and whether you take the shopping carts, you take whether the spring, like so the wire has got these varieties of products. Whereas if you take the stock, rod stock, for an example, rod stock for nails, for screws, for rivets, right, and for springs. So that's a rod stock, a different product. On the other hand, bar stock when you use, so you have metal bars for machining, you have forgings and other processes. You can start with the bar stock, which is produced by bar drying. Okay, so these are the very common products available. As far as the bar drying is concerned, it's quite different than the wire drying. The bar drying is accomplished as a single draft operation, right? That is, the stock is pulled through one die opening only, and the beginning stock has large diameter and is a straight cylinder, and therefore it requires a batch type operation. So the bar drying is generally produced in a batch operation, whereas wire drying is produced into continuous operation. Alright, so you can see here a bar drying bench. So the different components of the hydraulically operated draw bench for drying metal bars. You can see here the carriage, the drawn bars, the die stand, the starting work, the entry table, the hydraulic cylinders and all that. So these are very very important parts. So the bar drying bench is has got uh, such, like you now compare the features of a draw die. What a drying die must have, right? So that you can ensure that you have now good die life. So the features are that the entry region. So in the entry region you have funnels lubricant into the die to prevent scoring of the work and die. So that's the funnels lubricant. Then the approach part, that is the cone shaped region where the drying takes place, actual drying takes place in the approach region. Then the bearing surface, this determines the final stock size. The back relief or the exit zone provides that is provided with the back relief angle, that is almost half angle of around say 30 degree. And then you have the die materials. Usually in die materials that are very common is tool steels or cemented carbides. The diamonds are also used, but because the diamond is very costlier, you may use artificial diamond or CBN, cubic boron nitride dies are also very common. As far as the die material is concerned, let us see the overview of the die materials that is available. We have tungsten carbide as the lowest cost material, which has good stock resistance. It is easy of production. The large size of the die is possible, and it has a lower life expectancy. The natural diamond dies, okay, where you have the wear resistance, good wear resistance, gives excellent wear surface, the high thermal conductivity, and the longer life expectancy is obtained. Whereas it is susceptible to fractures from the shock or wear. Limited availability in the required high quality and quantity, and constantly escalating price is possible with the natural diamond dies. There is another variety we call as the synthetic single crystal dies, you know. So in synthetic single crystal dies, which is consistently uniform material made of, right? So this gives excellent wear surface. It has a high thermal conductivity, and it is predictable wear schedule it has, and has got uniform wear pattern, and this gives longer life expectancy. All right. So the larger size ranges are still very costlier at this time when you use single crystal material dies. All right. There is another very important class of the die material as the polycrystalline diamond. These polycrystalline diamond excels in life expectancy and has a wear resistance of the diamond because very high shock resistance of the carbides as compared to the carbides, high availability, cost effectiveness is there. So hard drying force and the smaller fines requires more filtration, and therefore that may be damaged by the temperatures above 700 degrees centigrade. So the wire surface conditions is less than from the natural diamond in when you use polycrystalline diamond. So these are some of the overview. One can make use of these some idea for selecting a good dye material. The tube drying, as I said, usual case which shows the tube drying operation. This can be with or without mandrel, as said. So the analysis part is quite different. We will discuss later the analytical part of the drying process, and one can know that when there is no friction in solid wire drying, one requires only maximum 50% reduction, not more than that. And the varieties of diameter, like for the tube drying, having different wall thickness can be produced from the same initial stock. Like this is again I am repeating for the stationary mandrel case, where the mandrel is attached and it stays with. This is the mandrel where it is a floating kind of mandrel thing, and this case where it is a moving mandrel type. So you get a different thickness of the material being produced. As far as the equipments, drying equipments are concerned, I said the equipment must have good dimensional control. It must give good surface finish. It must also be providing the improved mechanical properties of the drawn wire, and at the last, that the economic for the mass production must be ensured. So the cheaper cost, at the cheaper cost. So these are some of the things like the drying equipment is concerned. As far as the cold drying, as I said, it is to be straightened. So this is the straightening arrangement, and in case of wire drying with the multi-stage wire drying, this shows the two view of a multi-stage wire drying machine that is typically used in making of copper wire for electrical wiring, etc. So you can see the side view and the top view, and how the location of the die, then the speed control lever, and how does it then finally comes in and where it goes out. So that's a machine. As I said, before you start the wire drying operation, you have to prepare the operation. Okay, so you have to prepare the work, in fact the input wire or the work for drying to take place. So what are the three things that we have to remember is that annealing. If the stock is not very is hard, you need to anneal it. So once you anneal, you are going to increase the ductility of the stock, and the drying becomes easier then. Secondly, you have to clean the stock or work, so that to prevent the damage to work surface and draw life. Okay. And thirdly, you have to make the pointing. The end of the wire has to be pointed, so that to reduce the diameter of the starting end, to allow insertion through the draw die. Okay, so keeping this, as I said, you need to use some kind of roll straightening method like shown here. So this shows the schematic illustration of roll straightening of a drawn round rod, and you see the initially it gets straightened finally from the initial to the end case. In fact, because wire is being produced by pulling it through a die, and bar is usually produced in a batch mode and drying is in a continuous mode. So what happens to the stresses and strain development in wire drawing or rod drying process? So this slide shows the arrangement of to show you the nature of the stress and the strain development. So look at here the approach region. So the drying angle alpha, initial size is A0. So you look at the variation of the stress and drying pressure, the variation in the deformation zone especially, you can see on the lower side, that gives the effective strain variation in the deformation zone. So you see the nature is quite different. So the drying dies where the deformation is taking place, under that you have the stress that is the increasing in nature from the entry to the exit region of the approach portion. Whereas you have the drying pressure, it is increases linear in a different manner, and the strain variation is different. So these can be used for designing a die, and accordingly the die life and the stresses developed can be reduced and the die life can be increased. Therefore, either it is the case of wire drying or it is the case of rod drying. So this is what it shows, the stresses and the drying pressure for maximum reduction of area. So you see for the maximum reduction of area, the drying pressure is almost equal to K divided by n plus 1 and strain raised to the power n plus 1. N is your the strain hardening coefficient, and therefore for the maximum reduction in the area, so that the stress and with a proper that's a point near, so you observe the maximum pressure out of that. So as far as the mechanics of drying is concerned, a very simple mechanics. Suppose one wants what is the force required for drying. So as a simple case, what is the area in reduction in the drying? So how do you see? Because if you see the earlier figure, you have A0 and AF. So you can calculate the reduction R, that is A0 minus AF divided by A0, and that's the draft D can be calculated as D0 by DF. And when there is no friction and true strain, so one can find out without friction the true strain can be calculated as natural log of A0 by AF, and that's in terms of the reduction can be natural log of 1 by 1 minus R, and therefore the ideal stress sigma can be calculated as, that is the Y bar F natural log by A0 by AF, right? So if you take into the account the friction in case and the die angle, then this the stress can be Y bar F multiplied by 1 plus nu tan alpha. Nu is the coefficient of friction, phi is the die angle, and natural log A0 by AF. So that's the case, the ideal stress without friction, and when you take into account the friction, so this equation is valid. Usually the phi angle is taken as in this form, 0.88 plus 120, 12 capital D by L. Capital D is defined as D0 by DF by 2, and LC is defined as D0 minus DF by 2 sin alpha. So the drying force can be calculated. So the drying force capital F is what? It's AF sigma stress, drying stress sigma D, which is calculated there with friction. So you can use this is very popular equation as the drying force, where the friction is also there, and so as far as the maximum reduction is concerned, because it is always expected that the reduction per pass should be maximum. So let us see how much it is possible. It's a very interesting example. So if someone wants to have that the material is perfectly plastic material, in that case n is 0, you know, and suppose there is no friction and therefore there is no redundant work. So what is the drying stress? Simply it is y bar f natural log by natural log a0 by af, and therefore that is y natural log a0 by af, and therefore y natural log 1 by 1 minus r, and that is what is y. Then natural log a0 by af is natural log 1 by 1 minus r, and that is 1. So when there is no friction, no redundant work, so you have a0 by af is equal to 1 by 1 minus r, and that is E, and that's how the strain, the true strain is maximum is equal to 1. So if it is 1, so the maximum possible area ratio is a0 by af, and that is equal to E, and that is comes out to be 2.7183, and therefore we have got the maximum possible reduction. So the maximum possible reduction is nothing but E minus 1 by E. Alright, because E is what? The A0 by AF, and that gives 63%. So the maximum possible reduction without friction with a perfectly plastic material where there is no strain hardening, we have 63%. Alright. Likewise, you may have a analysis for drying, like the slab method if you use. So this slide shows a usual slab method you can use by taking different slabs, and rod drying, analysis of the rod drying can be performed. We will discuss this issue later, and because one can take the equilibrium equation and the volume within the two planes, and across the x-axis, that is x and dx from the conical die faces, and one can find out. So we would take the analysis for the solid rod drying and the tube drying in the next lecture. The only thing is to see that the wire drying is very widely used. The wire can be drawn of copper, which is of even the hair size, hair diameter size. It can be drawn as a rod as well. Okay. So there are many other ways. So the metal forming, you can even go for warm wire drying, shaped wire drying. We will discuss these issues later. The only thing to remember in wire drying is that the speed and the cost of the die. So the whole attention today in the market is the reduced die having a higher die life. With the market of the dies, because it is expanding very high, there has been application of CAD/CAM methodology for producing these dies. Alright, so we would continue this lecture, no doubt, and we would also see some of the problems if time permits. So I would like to thank you for your patience, and hopefully we will meet again to discuss the other portions like the analysis etc. of the wire drawing process. So thank you once again. Thank you all of you.